Okay, I think this is what we want. Okay, so we're doing Bootstrap. We're talking Bootstrap today. So on Wednesday we did. What did we cover on Wednesday? All right, settle down, settle down. Randomization tests. Okay, and we said we can use randomization tests. What has to be true about the data? If we're gonna re-randomize our data, what needs to be true about it? Exchangeability, right? And when is exchangeability? When does that apply? If there was random assignment in our process to gather our data, there was random assignment being used, right? And we said if random assignment is used, then the data should be exchangeable, and if exchangeability is true, then we can do a randomization test. And a randomization test just involves kind of re-randomizing our data and then sorting them into the different groups and seeing if the, whatever we're looking at, if that's still true or not. Okay, today we're going to do Bootstrap. And Bootstrap can be used in the other scenario. Okay, so if we don't have random assignment, what's the other thing that we might have regarding our data? What's the other random thing? Random sampling, okay? So if we have random sampling, if our data was obtained via random sampling, then Bootstrap is something that could be used. Okay. All right. Right. If you have random assignment, we'll do, you can do a randomization test. If you have random sampling, then you can do Bootstrap. And if you have both, then you can choose depending on, I guess, which aspect are we trying to work with. Okay. So bootstrapping, it comes kind of from the old phrase, pull yourself up by your bootstraps. And I don't know if this is true. It says origins of the phrase are disputed. Citation needed. Maybe it comes from a German folktale about the hero who was stuck in a swamp, and to get out, he pulled himself out by his bootstraps, and he got himself unstuck from the swamp. Only a folk hero can do that, but this guy did. All right. Bootstrapping in our context is a resampling method that we can use to test hypotheses or make conclusions about the population without the need for additional data. So, when we did the central limit theorem and all of that, we are making assumptions about the shape of the sampling distribution. The whole point of the central limit theorem is that the sampling distribution looks like the normal distribution, right? And when we do Bootstrap, we don't have to gather any more data, and we're going to try to figure out what the sampling distribution looks like just by resampling our very own data. And this feels kind of like pulling yourself up by your bootstraps. You're not looking at anything on the outside, you're just looking at the data itself. And there's parametric bootstrap and non-parametric bootstrap. And in my opinion, parametric bootstrap is not as interesting, but it's there, and so we got to cover it. Okay. All right. So I think I've said this already, but bootstrap resampling versus the randomization test. Okay. So if the data has been obtained via random sampling from the population, you can use Bootstrap. And if it was obtained via an experiment where random assignment was used, we can use a randomization test. And in both cases, what we're doing is we are simulating many instances where the sole source of variation in our statistics is random chance. So our computer will be the source of randomness, the source of random chance here, and it will serve as a way to generate a scenario that would be true if the null hypothesis is true. Okay, so we are generating other instances under the assumption of the null hypothesis. Okay, so how does parametric bootstrap work? With parametric bootstrap, we're going to make assumption about the population. Specifically, we're going to say that the population follows a particular parametric distribution. So maybe we're going to say the population is the normal distribution, or the population is, I don't know, a Poisson or log normal or chi-squared distribution, you know, one of those crazy distributions you learned about. You're going to say, I'm going to make the assumption that the population follows this distribution. This is my model for how my data is being generated. This is my vision for how the data is being generated, and we're going to say that this works this way. And so you use a parametric model there, parametric distribution, and we just generate random samples from that population. Okay, so R has some nice built-in functions. R can generate random values from a normal distribution. R can generate random values from a exponential or binomial or Poisson or whatever it might be, and you do that. And if R doesn't have that thing built in, then you might have to figure out some sampling method to generate data from some other distribution, right? So like in like the F distribution. Do you guys learn about the F distribution? How do we generate values from an F distribution? It's a ratio between T distributions, right? You got a T with V1 degrees of freedom and a T with like V2 degrees of freedom, and basically you would I don't know if there's, I think there's probably a random F distribution, but if there's not, you would just generate two T distributions and then take those two random variables and then take the ratio between your F. Okay, so you basically just simulate random samples from something, and then you compare that to your results, and you say, well, how often do I get the results that I have? We'll do some demos, okay? So that's parametric bootstrap. So instead of using math, you're using the random samples here. Okay, non-parametric bootstrap. This is a little bit more interesting here. We're not going to make any assumptions about the population at all. What our key assumption is that the sample that we have, the sample of data that we have, is a random sample drawn from the population. And if the random sample that we have is a random sample drawn from the population, we can expect it to be at least somewhat representative of the population. And you know, you can imagine, let's say we want to simulate or generate a sampling distribution. And a sampling distribution is the idea of going back to the population and just drawing many different samples from the population. Well, how can we, if we don't have the original population, how can we draw new samples from the population that doesn't exist for us? Well, what we do is we say, I'm going to pretend that my current sample is representative of the population, and therefore if I want to I'm going to create a fake, like a pseudo actual population by just taking my current sample and making a ton of photocopies of it, okay? And you just make a whole bunch of duplicates, right? So, and now I have the population, and then like not the actual population. It's like it's a you know, poor man's version of the population, but it's it's going to stand in there, and then we're going to just draw from that thing. Okay, so that's effectively what we can do is, rather than actually duplicating the data to create in our stand-in population, we just draw with replacement, right? If you draw from a sample with replacement, you are effectively making an infinite number of copies of that sample, and you're drawing a sample from that. So that's what non-parametric bootstrap is. We just draw samples with replacement from the very data that you have, and that's effectively just creating an infinite number of duplicates of your current sample as a stand-in for the actual population. And then you do that a whole bunch of times, and you can generate your sampling distribution. Here, let me pull out my tablet. Okay, this is a different class. I'm sorry? Something's wrong with my, fix my pen. Okay, so just a recap. Let's say, what is a sampling distribution? The idea is you've got this big entity called the population. This is well, and the whole idea is that the population is too big for direct study, right? And so what we do is we just draw from the population, we take out a sample, and from our sample we summarize it with an X bar. Okay, and then maybe I go back to the population and I draw another sample, and this sample we summarize with another X bar. We draw another sample. X bar, okay? Each sample, okay. Each sample is obtained via random sampling. Okay. We keep track of every single X bar. And kind of the resulting histogram of all the different X bar values that we get is our sampling distribution. Okay, and so this sampling, that's technically an approximation, sampling distribution of X bar. Okay. Stats. 2. So that's your general sampling distribution, okay? So this assumes we can go to the population over and over and over again, right? Okay, so Bootstrap is, can we still get this sampling distribution when we no longer have access, or like if we never had access to the population, right? Can we still, Bootstrap says, can we still get the sampling distribution if we never had access to the real population? Okay, that's what we want to do. All right, so the parametric and the non-parametric bootstraps are just basically two approaches for this, okay? So parametric bootstrap. All right, so what we start with a random sample. This is what we have. So what can we do? Well, what we'll do is we will we'll summarize this. We'll get an X bar, maybe we'll get an S. We'll get, you know, some other summary statistics. Okay. And then we go, okay, well, I believe the population is ... and then maybe we will say is, you know, whatever word you want to say. Here we'll say normal with mean equal to X bar and standard deviation equal to S, all right? And so, you know, my population then will look like this. So my population if my assumptions are correct. Okay, and then the bootstrap part is, so we have our assumed population. And then we'll just draw sample 1, sample 2, sample 3, etc., 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 etc. Each of these generates an X bar. Okay, you got lots of X bars, and then you gather all of these into your sampling distribution. Generated X bars. Okay. Does that make sense as far as parametric bootstrap goes? So we'll just, so you look at your sample, and based on the summary statistics in your sample, you're making up a new thing, right? So it doesn't, you know, it doesn't have to be normal. Maybe someone else says, I think it's exponential or something, you know? Whatever you have, okay? Or exponential, or, you know, log normal, or whatever you have, okay? Et cetera, et cetera, et cetera. So that's parametric bootstrap. We don't have access to the population, so we just make some kind of parametric assumption about the shape of the population. Yeah?
So the assumed population will be normal exponential.
Or whatever it is, right? You just pick some distribution, right? And if your assumption here is bad, then your results are going to be bad. Okay? I mean, that's all of life. If you made bad assumptions about your life, then everything else is going to not work out right. So it applies for. Sorry, I didn't mean to like. Too real. You know, so here in this example, I said I'm going to assume that the population is normal, right? But basically, you're just going to assume that the population is some sort of parametric distribution that you've learned about or will learn about or can look up, right? There's lots of distributions, right? And distributions can really be any shape you want. What's the requirement for a distribution? Yeah. Basically, the whole thing has to be positive, and the entire area has to equal 1. Okay? And that's it. You can have any crazy shaped function, and as long as it meets those two criteria, that the function is positive for the the support or the domain that you're interested in, and as long as the total area integrates to 1, that qualifies as a probability distribution. And you can say, I think my population looks like this thing. Okay, great. And then you just whatever your assumed population is, you just generate a whole bunch of samples randomly and use that to generate your sampling distribution. Yeah, question?
Do you assume that population has the mean and standard deviation that you have from your sample?
Well, you want to somehow tie the population you're making assumptions about to the sample of data that you have, right? You want the assumptions because the whole idea is the assumptions you are making are somewhat based in reality, right? And so generally, we say, okay, I'm going to look at my data, and based on the data, this is going to help inform what my assumptions are, right? And so you probably make an assumption about what the shape is. In this case, we're going to assume it's unimodal and symmetric, and the normal distribution is a good example of that. And then we will define the shape using the mean and standard deviation. But if you're going to do an exponential distribution, right? An exponential distribution has, what's the parameter that defines the exponential distribution? Lambda, right? Which is basically the mean. And so you would find that the equivalent statistic from your data, and you would use that to generate your assumed population. Yes?
How would you be able to tell that your assumption is not correct?
Yeah, it's hard. The only way you can find out your assumption is bad is when you come up with data later that contradict your earlier assumption, right? Until that happens, all you can do is, I hope, and that's. But yeah, if we knew right away, like, I'm going to make an assumption, and if we could easily test that right away, then we would rarely make bad assumptions. But that's the thing. So generally you would make, well, I mean, you might be able to test right away. If the assumption you make doesn't fit the data that you have right now, then that's probably a bad assumption to make. But if it's like reasonable, you don't know if it's good or bad until you collect more data that strongly disagrees with it, right? So maybe you assume it's normal, okay? That might be a reasonable thing, but then later on, as you're collecting data, you get something that's like 6 standard deviations away, right? Then you go, oh, maybe it's not normal. Maybe it's Cauchy or something, right? Like a T distribution with 1 degree of freedom is a Cauchy distribution, which generates. Am I talking nonsense here?
Yeah.
Okay. So the T distribution is just a relaxed normal distribution, right? So the normal distribution, we say things like 95% of the data is within 2 standard deviations, okay? And then the T distribution just relaxes that and just says, okay, 95% of the data is going to be within 2.5 standard deviations or 2.7 standard deviations, as your degrees of freedoms go lower and lower and lower and lower, right? And so when you get down to degrees of freedom equals 1, we give it a special name, and it's called the Cauchy distribution. And it looks a lot like the normal distribution, but the tails are like super wide. Like it's a lot flatter. And so you get like it's totally normal or totally not unusual to get an observation that's 6 standard deviations away from the mean with a Cauchy distribution. And in fact, the tails are so wide that you no longer are able to calculate the mean because the integral doesn't work out. But anyway, not important.
So what's the purpose of this? What are we doing? Like, are we testing something?
Yeah. Basically, like if we wanted to do hypothesis testing, right? And we say like, is my sample unusual, or do I have evidence of something, blah 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 blah. Like, we need to have some idea of what the sampling distribution looks like, and so this allows us to get an idea of what the sampling distribution looks like using the current data that we have. Okay. Yes.
Also, if we form our assumption on the population using the sample that we have, isn't like the sampling distribution in this case, like wouldn't it be centered around the X bar?
Yes, exactly. It would be centered at X bar. And so you would not be able to test hypotheses about X bar or about mu because you don't have that information. But you can use this information to give you it's going to be useful to give you ideas what the standard error is, or other aspects are going to be useful. Okay. No, that's very good. Okay, so that's parametric bootstrap, and then non-parametric bootstrap. Again, we're just trying to answer the question: what does my sampling distribution look like if I can't see the population? So this is non-parametric bootstrap. You have your sample, and then you put it into the cloning machine. And then out comes the population, which is just infinity duplicates of the sample, right? So it's like if we want to do research on the statistics department or something like that, we could just take this classroom and like make duplicates of it, and that would be a quote stand-in for what the population is or something. General population of the statistics department is. Huh? Huh?
Don't you have a population?
Yeah, we do. I mean, but like, let's say you don't, right? So in this case, we only have a sample. We clone it, and then now we have the population. Now that we have the population, then we can just draw sample 1, which produces an X bar, and then we draw sample 2, which produces X bar, and we draw sample 3, etc., etc., etc. Okay? Okay, and again, we keep track of all of these. species. Okay, and then you get something that resembles your sampling distribution, whatever it might be, okay? Okay, so that's what we have, non-parametric bootstrap. Okay, I'm going to use an example from the textbook. Is it okay? Can I go back to the slide here? Okay. Okay, so this comes from the Ziefler textbook on comparing groups. And okay, so we're looking at the Center for Immigration Studies at the U.S. Census Bureau, and they reported shifts in the ethnic makeup and the immigrant population, but still Latin America and Mexico specifically remains this country's greatest source of immigrants, okay? And although the average immigrant is approximately 40 years old, large numbers of children who enroll, there are many children who enroll in U.S. schools upon arrival, and their subsequent educational achievement affects not only their own economic prospects, but also those of their families, communities, and the nation as a whole. These two researchers, Stamps and Bohan, studied the educational achievement of Latino immigrants by examining a random sample of the 2000 decennial census data. So it's a little bit old by now, but year 2000. And we're going to look at a subset of that in this file, latinoeducation.csv. And in particular, we'll look at this one research question, which is whether there is a link between where the immigrants originated and their subsequent educational achievement, okay? So as far as the data goes, they're gonna say, is the immigrant from Mexico or other Latin American country, okay? And then and then somehow they put the achievement, and I don't know what these, I don't have the codex here, like I'm not able to go from this and actually tell you what it means, but they put the achievement level on a scale of 1 to 100, 100 being higher levels of educational achievement and 1 being the lowest. And that, I don't know what is a 50 on the scale. Is that college or high school? I don't know. I don't know what that means, but that's what we have, okay? And so the thing, and there's other information here, but the thing that we're going to be looking at is their achievement. Is there a relationship between that and whether they came from Mexico or no? Okay, so we'll just read this in, and so we've got I think just 150 people, immigrants coming to America, and we looked at this, and we'll look at their achievement score and whether they are from Mexico or not. Okay, so we'll ignore the other columns. Okay, and then we want to know, is there some kind of relationship between achievement and this column, whether they are from Mexico? And so so when we do the mean of non-Mexican Latino immigrants, the mean achievement score, mean of the achievement scores is 64.5 with the standard deviation of 13, and then for those from Mexico, the mean achievement is 58.6, standard deviation of 15.6. Okay, so and then if we just did some, again, exploratory analysis, I don't know why that's hovering on top of here, but this is a box plot. This is what it looks like. So this is the upper ones for Mexican immigrants, and this is for non-Mexican immigrants. Okay. And if we did kind of a why is this hovering like that? Did kind of a density plot. Blue is for Mexico and pink is for non-Mexico. Okay. All right, and then the traditional analysis would be a t-test, and we would just do achievement as, can that be explained by the variable Mexico? All right, and we get a p-value of about 3%, okay? So, I don't know, what does that mean? It's like, it's just under 5%, but it's not like super convincing, okay? But anyway, that's where we are here. Let's take a look at this in RStudio as well. Okay, so I'll bring this in, okay? Okay, so if we wanted to do parametric Bootstrap, okay, we could just take so we'll just summarize achievement. Okay, so I'll do a Latino $ achieve. Let's do, because I like to apply. All right. Okay, so this is the overall mean, and then let's get the standard deviation. Okay. So we'll call this M, and we'll call this S. I don't want that. Okay. So I've got, here's my mean. I've got my standard deviation. These are just from the entire. If we pulled everyone together. Sorry, are there any questions so far? So here I'm just getting summary. This is for parametric Bootstrap. Okay, and then so now we will define our normal distribution, and what we'll do is we'll get 150 values drawn from M with a mean equal to M and standard deviation equal to S. Okay, and so what I should also do is what are the names again? So so in our data we have 116 from Mexico, meaning 34 that are not. Okay, so we can do this a few ways. One is I can just draw 116, and this will serve as Mexico, and we'll get 34 values drawn from a mean and standard deviation. Okay, and then we can just ask, what's the mean for this is from our randomly sampled values. Okay, and so we get just two different values here. Okay, and so the question is in our data we got, okay, so we got a mean of 64.51 and 58.59. So our observed difference is going to be do results, and I think, is that just 2, 1, or no, 1, 2. There's numeric. Okay, so my observed difference is going to be this minus this, right? So I'm observing a difference of, 64.51 minus 58.59. Okay, I'm getting a difference of 5.92. This is going to be my observed difference. And so the question is, how often do we get something like that if my only source of variation is the random sampling process, right? So if I do random, and I calculate the difference of these means, this time, this is the difference that I'm getting. So what I'm going to do is I'm going to just put this into a loop, and I'll do for I, and I don't know, we'll do 10,000. We'll do 10,000 of these, and every single time we'll just generate 116 from the population and 34 from the other, and then we'll take the difference, and diffs will be 10,000. We'll repeat these 10,000, and we'll just store this into diffs I. Okay. Does this make sense what I'm doing? Okay, so because under the null hypothesis, we're going to say that there's no difference in the education achievement between immigrants coming from Mexico and immigrants coming from other Latin American countries. So basically, they are both coming from the same normal distribution here that has the same mean and same standard deviation, and we're going to approximate. We're going to just say the mean is just the overall mean achievement score and the overall standard deviation. Okay, so we're going to do that. And then we're just going to try this 10,000 different times and just see what kind of results we get. Okay, now we're done, and let's take a look at the diffs. So I can do histogram of diffs. All right, that's what we get if I do the summary of diffs. Again, we expect something around 0, and that is what we observe. And what we want to know is how often do we get differences. So the largest difference we observed was 11.52. Our observed difference was 5.921. How often do we get something like that? Okay, so I'm going to just say diffs greater than or equal to observed diff, right? So this is going to be a vector of true falses, and then so if I just ask what's the mean of this, this will just tell me how many times this happened. Okay, this happened about 237 times out of 10,000, so about 2% of the time, 2.37% of the time. And so we have to decide, is this enough for me to conclude that there is a difference? And we have to say, maybe not, I don't know, okay? So this would only happen by random chance about 2% of the time, okay? Because this is what we did, right? We did this by random chance, and when we did it by random chance, we got differences of 5.92 or greater 237 times out of 10,000, okay? So this stands in as a empirical p-value. Oh man, we didn't even get to do the non-parametric one. Okay, well I'll write some code for non-parametric annotated, and I'll post that online for you guys to read. Okay, but this is the parametric bootstrap, and then we'll do one for the non-parametric. Okay, all right. Have a great weekend, you guys. We'll see you Monday.